Welcome to the deep dive.
It's great to be here.
Today we are questioning a zero, which in physics is usually a safe place to be, right? Zero is comfortable.
It's the best number. It means nothing to see here, symmetry is working, things cancel out.
You can move on.
You get to go home early if you prove something is zero. It saves you pages and pages of algebra.
Exactly. But what if the zero is actually zero?
Uh-oh.
We're looking at a paper today titled Single minus gluon tree amplitudes are non-zero. And just from that title alone, if you're a physicist, you're probably spitting out your coffee.
It's a very provocative statement. I mean, it's basically saying, you know that thing you've all been ignoring for 40 years because you thought it was empty?
Yeah.
It's actually full of information.
And the team behind this is a who's who. We're talking researchers from the Institute for Advanced Study, Cambridge, Harvard, Vanderbilt. But there's another name on this author list that really jumps out.
OpenAI.
OpenAI, that's the wild card.
It really is.
Yeah.
And the paper itself is a wild card. It takes a specific type of particle interaction, something physicists have, just assumed vanished, and it proves that if you look at it from a very specific, almost weird angle, it's there.
It feels like finding a secret room in a house you've lived in your whole life.
Yeah.
You thought it was just a blank wall, but you push on the right brick, and suddenly there's a whole library.
That's a surprisingly good way to put it. And this secret room suggests our map of the quantum world, specifically the laws of the strong nuclear force, is missing some pieces.
Or we've just been reading the map with one eye closed.
Exactly.
Okay, so before we get to the AI and the secret rooms, let's lay the foundation. We're talking about scattering amplitudes. If I'm trying to explain this at a dinner party, how do I describe them without clearing the room?
Think of them as the source code for a collision. You take particles, like gluons,
Which hold the nucleus of an atom together.
right, the carriers of the strong force, and you smash them together at near light speed. The scattering amplitude is the mathematical probability of what comes flying out of that crash.
It's the prediction engine for a particle accelerator.
It is, but the engine is notoriously difficult to run. Historically, we use Feynman diagrams. You probably see them on T-shirts. Little stick figures.
The little doodles, yeah. Squiggly lines and straight lines.
They look cute, but they are computational monsters. I mean, if you have two particles hitting each other, it's easy. But when you add more particles to the collision, the number of diagrams you have to draw and calculate grows faster than exponential.
Faster than exponential. So adding one more particle doesn't just double the work.
It explodes it.
Yeah.
Exactly. It becomes a computational brick wall. We're talking thousands of pages of algebra for one single collision.
Wow.
But, physics has a way of surprising us. In the past, researchers Park and Taylor, the famous ones here, found that if you trudge through all that math for a specific setup called MHV,
MHV. What is that?
maximally helicity violating.
Sounds intense.
It does. But the result was just shocking. Millions of messy terms just canceled each other out. All that algebra just vanished, leaving one tiny, elegant, one-line formula.
Like the clouds parting.
It really was. It showed that the final answer was simple, even if the method to get there, the diagrams, was a total mess.
Which brings us to today's topic. The single minus amplitude. Let's define the setup here.
Right. So gluons have a property called helicity. You can think of it roughly like spin. It can be plus or it can be minus.
Okay.
The MHV case I just mentioned had 2 minus particles and the rest were plus. This paper, though, it focuses on single minus amplitudes.
So just one.
Exactly, one gluon with minus helicity, and all the rest could be 5, could be 100 or plus helicity.
And the conventional wisdom on that was?
0. The answer is 0. Gone.
Why? Was it just a guess? Or did someone actually calculate it?
It was a very educated deduction. It's based on something called a power counting argument.
Sure.
Without getting too bogged down in the math, imagine you're trying to build something. You have polarization vectors, think of those as your bricks.
Okay, bricks.
And you have momentum vectors, that's your mortar.
Bricks and mortar. Got it.
In this specific single minus case, the argument was that you just don't have enough mortar to stick the bricks together. There literally aren't enough momentum vectors to contract with all the polarization vectors.
So the inventory list says you can't build the wall.
Exactly. For what we call generic kinematics,
Yeah.
Particles flying around in normal 3D space like at the LHC, the math just collapses. It goes to 0. The argument holds up.
But the title of this paper is Single minus gluon tree amplitudes are non-zero. So how do you get a value out of something that mathematically shouldn't exist?
You cheat the geometry.
You're gonna cheat the geometry. Okay, go on.
The authors found a loophole by looking at a very specific regime called half-collinear. Now, the paper gets pretty poetic here. It talks about restricting momenta to a one-dimensional null circle on the celestial torus.
All right, hold on. Celestial torus sounds like something out of a fantasy novel, not a physics paper. Can you translate?
It is a bit magical, isn't it? It's really just a fancy way of talking about the angles that the particles come out at. Half-collinear just means you're forcing the particles to line up in this really rigid, specific way. You're not letting them scatter randomly.
But if the math says zero, shouldn't it be zero no matter how you line them up? I mean, zero is zero.
Usually, yes.
Yeah.
But here's the twist. To make this alignment work mathematically, you have to leave our standard space-time. You have to work in something called Klein space.
Klein space. That's different from the Minkowski space we usually do physics in.
Oh, very different. Minkowski space, our universe, has 3 dimensions of space and 1 of time. We write that as a 3-1 signature. Klein space has 2 of each, 2 space, 2 time.
2 dimensions of time. I can't even picture that. What does that even mean?
You don't really have to picture it, which is good. You just have to use it mathematically. It's a tool. It lets you treat momentum variables in a way you can't in the real world. And when you do that and you line up these particles in that half-collinear way, something strange happens to those bricks we talked about. The polarization vectors.
The ones we didn't have enough mortar for.
Right. In this specific limit, those vectors become singular. They blow up to infinity.
Wait, so the amplitude is trying to be zero because of the missing mortar, but another part of the equation is going to infinity.
Exactly. It's a tug of war. And in calculus, 0 times infinity is the ultimate who wins. It's an indeterminate form. It can be anything. And here, it creates a finite non-zero value.
So the zero and the infinity cancel each other out, and what's left is this new physics.
That's the loophole. It's beautiful.
That is incredibly sneaky. It's like finding a blind spot in the laws of physics where the normal rules just don't apply.
It is.
Yeah.
It's a mathematical jujitsu. You use the force of the singularity to flip the zero into something real.
Now, finding a blind spot like that usually takes incredible intuition. You have to know exactly where to look, and this is where the story takes a turn that I think is going to define the next decade of science. The authors didn't just figure this out on a blackboard.
No, they had help. Significant help.
The paper states, and I'm quoting here, that the key formula for this non-zero amplitude equation 39 was first conjectured by GPT 5.2 Pro.
It's a stunning admission to see in a top-tier physics paper. We're not talking about using AI to, check your grammar. We're talking about symbolic discovery.
GPT 5.2 Pro. And then it gets even better. It says the conjecture was subsequently proven by a new internal OpenAI model.
This is a big deal. This changes it changes the workflow of theoretical physics. The AI didn't just simulate something. It looked at the patterns in the data and just guessed the underlying law.
Okay, but let's play devil's advocate. AI hallucinates. It makes stuff up. It can sound incredibly confident when it's just plain wrong. How do we know it didn't just spit out some fancy-looking equation that means nothing?
That is the crucial part, and the paper is very careful about this. The physicists didn't just trust the bot. They used the AI as an idea generator, but they acted as the filter of truth. They verified the solution using something called Barron's Geel recursion.
Barron's Geel recursion sounds complicated.
It is. It's a rigorous recursive method to sum up all those millions of Feynman diagrams we talked about. It's the gold standard. They basically ran the AI's homework through a supercomputer to prove it actually worked.
So the AI provides the spark, the aha moment.
And the human provides the rigor to prove it matches reality. It's a collaborative loop. The AI spots a pattern a human might miss in all the complexity, and the human verifies the pattern obeys the laws of nature.
So let's look at the pattern it found. Because if Feynman diagrams are exponentially complex, and this was supposed to be impossible, I'm expecting this formula to be just a monster.
And that's the absolute shocker. It's not. It is so simple, almost suspiciously simple. The paper describes the answer as piecewise constant.
Piecewise constant, so it has steps, like a staircase.
Or mosaic. Yeah, the authors use very visual language. They describe the amplitude as existing in chambers separated by walls.
What are the walls?
The walls are just mathematical boundaries where sums of momenta become orthogonal, where they hit a specific geometric limit. But inside the chambers, between those walls, the value of the amplitude is constant. It's stable.
Just flat.
It's flat. And in one specific region they identified, they call it region R1. It gets even more ridiculous. The amplitude only takes the values of +1, -1, or 0.
Wait, hold on. We're talking about quantum chromodynamics,
Right.
the strong force. These calculations usually involve complex numbers, polylogarithms, a complete mess of Greek letters, and you're telling me the answer boils down to an integer.
Just +1, -1, or 0. That's it. Technically, it's a signed product of projection operators, but the output is just an integer.
That feels wrong. It feels too simple. It's like finding out the answer to life, the universe, and everything really is just 42.
It feels like we cheated complexity. We went from faster than exponential chaos to just counting 1 minus 1. It suggests that underneath all the frothing mess of quantum mechanics, there's this crystalline geometric structure that is remarkably clean.
But how does a simple integer like +1 obey all the complex rules of physics? I mean, these particles have to follow conservation laws, symmetries. Doesn't simplifying it this much break something?
You'd think so. And that's why the verification section of this paper is so important. They ran this simple formula through a whole gauntlet of physics stress tests. It's like a checklist of impossible things the formula had to satisfy.
Okay, let's go through the checklist. First up, Weinberg's soft theorem.
Right. This is a fundamental consistency check. Weinberg's theorem tells you what happens when one of the particles' energy goes to 0, when it becomes soft. Physics dictates exactly how the formula has to behave in that limit. It's a rigid law. And the AI's integer formula passed perfectly. Even though it looks static, when you push it to that limit, it behaves exactly as physics demands.
What else?
Cyclicity. Since these are color-ordered amplitudes, if you just rotate the particles, move particle 1 to spot 2, 2 to 3, and so on, the physics shouldn't break. The formula has to respect that symmetry. And then there's U1 decoupling. That's a consistency check for photon-like behavior. Basically, if you swap a gluon for a photon, it shouldn't interact in the same way. The formula respected that too.
And Klein-Keif relations.
Yes, those two. These are really complex relations between different orderings of the particles. It passed everything.
So here's the big question. When you look at the raw formula, this product of projection operators, is it obvious it would pass these tests?
Not at all. And that's what the paper calls non-trivial.
Right.
If you or I just wrote down a random formula with +1 and -1, it would fail these tests miserably. The fact that this specific geometric arrangement satisfies the deepest symmetries of the universe, that's what tells us it's real.
It's not just a math trick.
It's capturing something true about the physics.
It's like a key that fits 5 different locks at once. If it opens all of them, it's probably the right key.
That's a great analogy.
So we have a formula that works. We have a non-zero value where we thought there was nothing. Why does this matter? Is this just a bit of bookkeeping for particle physicists, or does it change how we understand the universe?
Well, it connects to a much bigger puzzle. It involves something called self-dual Yang-Mills theory, or SDYM.
Okay, we're getting into the deep end now. SDYM.
Think of it as a toy model of the strong force. It's a restricted, idealized version of reality that often reveals hidden truths. But there's been this tension in SDYM for a long, long time.
Attention.
Yeah. So on one hand, the classical solution space of SDYM, the non-quantum level, is known to be extremely rich. It has complex solutions, beautiful geometry, twisters, all this really cool stuff.
Okay.
But on the other hand, the tree diagrams, the quantum part, were thought to be trivial, just boring, almost empty.
So the classical map was a lush jungle, and the quantum map was a barren desert.
That's the perfect description. And it never made sense. The quantum theory should inherit the richness of the classical one. This paper suggests that the missing richness was hiding in these zero amplitudes all along.
The single minus amplitudes.
Right. By showing these are non-zero and that they have this complex chamber and wall structure, it finally bridges that gap. It shows the quantum side is just as rich as the classical side. It makes the theory whole again.
It's so satisfying when puzzle pieces click together like that. But let's zoom out. We often hear about the standard model being the most successful theory in history. I think the paper even says Feynman diagrams match experiments to, 14 decimal places?
Unprecedented precision. It's the most precise theory humans have ever created, period.
So if we can already calculate things to 14 decimal places, why are we rewriting the math? Why hunt for region R1 in Klein space?
Because there's a huge difference between getting the right answer and understanding why it's the answer. Feynman diagrams are a brute force method. They obscure the machinery. It's like calculating the area of a circle by drawing a million tiny little squares and adding them all up.
You'll get the right number eventually.
You will, but wouldn't you rather just know R222?
Always.
That's what this is chasing. The authors believe this piecewise constant simplicity is a glimpse of the R22 of particle physics. They think if we keep pulling on this thread, we might replace the faster-than-exponential nightmare with a new formalism based on simple integers and geometry.
Calculating smarter, not harder.
And doing it with a new partner.
Yeah.
The fact that an AI spotted this structure, that's the other huge takeaway. We might be entering an era where we don't just use computers to crunch numbers, but to tell us which numbers matter in the first place.
It really feels like we're on the edge of a fundamental shift. We started with a zero that wasn't zero.
We traveled through 2 dimensions of time in Klein space to find a loophole.
We watched GPT 5.2 Pro basically conjecture a new physical law.
And we saw that law collapse the chaos of quantum mechanics into simple integers.
It really makes you wonder how much of the complexity of the universe is actually real, and how much is just us using the wrong math to describe it.
That is the question, isn't it? Maybe the universe isn't complicated. Maybe we're just looking at it from the wrong angle.
And maybe next time, we'll have the right AI to point us in the right direction. Thanks for listening to The Deep Dive.
Until next time.